In this video, I will talk about the parallel combination of capacitor. So we have three capacitors C1, C2 and C3, and they are connected in parallel. When the capacitors are connected in the parallel, then the potential across each capacitor is exactly the same. And the total capacitance of the system or the combination of the capacitor is equal to the algebraic sum of each capacitor. This is the CP. Here stands for the total capacitance in parallel combination. P stands for parallel, which is equal to C1 plus C2 plus C3. What does it tell you? That the equivalent capacitance is always greater than the individual capacitor in the parallel combination. And the other way of thinking, why does the capacitance increases? Because you can see now when these capacitors are connected in parallel combination, then the effective area, like if I connect them here, then the area of the capacitor increases. That means it has more ability to store charges, or in other words, the capacitance increases. Okay, because the total surface area of the plate increases, keeping the gap constant. Now, if each capacitor are different, then the charge stored onto C1, C2 and C3 will be different. Okay, but the total charge, then the total charge is given by this formula here. QP is equal to Q1 plus Q2 plus Q3. This is the total charge stored into the system or into a combination of the capacitor. The working voltage or the breakdown voltage of the combination of the capacitor, this is the working voltage of the combination, is that of a capacitor which has the lowest working voltage. And the reason is because all capacitors are connected in parallel. So let's say this one has the working voltage of 300 volt, this one has 100 volt, and this one has 200 volt. Then the working voltage of the system will be still 100 volt. Okay, if we apply more than 100 volt, then this capacitor will blow away. So it won't, and that's the reason we say that the working voltage of the combination is of the capacitor which has the lowest working voltage. Okay, even if the capacitor blows away, these two capacitors C1 and C2 will still be in the series combination, but that's a different story here. Okay, now let me explain this story by using this simulation. Here I have chosen three capacitors C1, C2 and C3. Okay, so C1, hey, let me zoom this one a little bit. The C1 has a capacitance of 10 microfarad, 10 microfarad and 10 microfarad. So as they are connected in combination, you can expect the total capacitor will be 0.3 times 10 to the or 30 picofarad. So this one is 10 picofarad, this one is 10 picofarad, and this is 10 picofarad. So the total combination is now 30 picofarad. Okay, now let me measure the potential. Let's say I'm applying 1.5 volt. If I measure the potential anywhere, then it will still read 1.5 volt. Let's say across, I'll just make this one positive and this one negative. So do you see the potential across the second capacitor is 1.5 volt. The same way it will be 1.5 volt, or even if I measure here, it has to be 1.5 volt because everything is connected in parallel combination. Okay, and now the stored charge. Now let me measure the stored charge. How much charge is stored here? Okay, so the total stored charge is given is 0.45. That means this is the Q1, Q2 and Q3, the combination of all charges. So the mm, this is all about the parallel combination of capacitor. The two things you need to understand is in parallel combination, the total capacitance always increases. The potential across each capacitor will be exactly the same, and the total charge is the charge of Q1 or C1, C2 and C3. The total charge is the charge onto the C1 capacitor, C2 capacitor and C3 capacitor, okay, which is given right here. So this is it for the parallel combination of capacitor. Any question? Please write down your question in the comment section below, and do not forget to subscribe my channel. Thank you so much.